So, we are discussing the quantization of radiation quantization of the Dirac spinner, and what we have done so far is we have constructed the linearly independent solutions, and then we have seen that the most general solution can be expressed as sum over S integration dqp over 2 pi cube m over omega p, then Cs p USP e to the power minus I p dot x plus ds dagger p vs p e to the power I p dot x, and similarly you have psi bar x, and what I have seen is that in order to get the Fermi Dirac statistics, we need to adopt the anti-commutation relation. So, therefore, what we have seen is that psi of x t psi dagger I times psi dagger is the conjugate momentum to the field psi. So, therefore, psi alpha x t psi dagger beta of y t is nothing but delta of x minus y delta alpha beta. So, this implies that the operators Cs and ds dagger, they satisfy the following anti-commutation relations: C R P C S dagger K is 2 pi cube times omega p over m delta p minus k delta r s, and a similar expression for the d's, and then all other anti-commutation relations vanish. So, what we have shown is that these relations here, this and ds p dr dagger k again is equal to the same thing. What we saw is that this is equivalent to this. You can also show, starting from this, that these anti-commutation relations are in fact satisfied. All you need to do is you need to have an expression for these operators Cs and ds dagger in terms of the field psi, which I will write it down here for you, and then you can verify that this is in fact true. Cs of p is equal to integration dqx us bar of p e to the power I p dot x gamma 0 psi, and ds dagger of p equal to dqx vs bar of p e to the power minus I p dot x gamma 0 psi. So, you take this anti-commutation relations, or you consider this, you substitute this for the Cs and ds, and then use this anti-commutation relations, you will be able to derive these relations. Anyway, so what we will do now is that we will we will consider the propagator for the Dirac spinner, and then we will derive an expression for the propagator. So, to do that, let us define psi plus to be this part here and psi minus to be this. So, you can write psi of x equal to psi plus of x plus psi minus of x. Similarly, you can consider psi bar of x, which is equal to sum over s dqp over 2 pi cube m over omega p Cs dagger of p us bar of p e to the power plus I p dot x, and here you have ds of p vs bar of p e to the power minus I p dot x. So, because of this e to the power I p dot x dependence, we denote this to be psi bar minus and this to be psi bar plus. So, therefore, psi bar of x again is psi bar minus of psi bar plus of x plus psi bar minus of x. Now, what we would like to do is we would like to derive this anti-commutation relation psi of x psi bar of y, where x is x mu is x t, y mu is just y t prime. So, these are not equal time anti-commutation relations. Time here need not be the same. We will derive it in terms of the components of the spinner. So, I will write it as psi alpha, psi bar beta, and you can see that this here is anti-commutator of psi alpha plus of x plus psi alpha minus of x with psi bar beta plus of x plus psi bar beta minus of x. Why? Thank you. Now, you can see that it is of course obvious. Psi plus actually here contains Cs and psi bar plus contains ds. Therefore, the anti-commutation of psi plus with psi bar plus is 0. Similarly, the anti-commutation of psi minus with psi bar minus is 0. So, all you will be left with is psi alpha plus of x, psi bar beta minus of x, and then here psi alpha minus of x and psi bar beta plus of y. That is what you will have. So, now let's derive the expression for one of these relations, which we will compute this explicitly and then I will just give you the answer for this expression. To do that, let us explicitly use the expression for psi alpha plus and psi bar beta minus. Okay. So, if we do that, then what I will get is, so evaluate psi alpha plus of x, psi bar beta minus of a y is just equal to integration d cube p over 2 pi cube m over p 0 and d cube p prime over 2 pi cube m over p 0 prime. Then I have to carry out the spin sum. So, sum over r and s, and Cr of p, Cs of Cs dagger of p prime, this times u r alpha of p, u s beta of p, u s bar beta of p prime, and e to the power minus I p dot x plus I p prime dot y. Right. So, this I obtain by straightforward substitution. Now, I will use the anti-commutation relation for CRP, CS dagger P prime, and then I will carry out the P prime integration. What I will get as a result is integration d q p over 2 pi cube m over p 0, and the anti-commutation here will cancel m over p 0 prime and 2 pi cube, and the delta function that comes here will remove the dqp integration. So, all I will have is sum over s u s alpha of p u bar s beta of p e to the power minus I p 0 t minus t prime e to the power I p dot x minus y. All right. So, what is this quantity here? Good. So, this of course, we have seen it many times. This we can substitute the expression for this dqp over 2 pi cube m over p 0, and this one here is p slash plus m, alpha beta component of p slash plus m divided by 2m. This times e to the power minus I p dot x minus y. Okay. So, this looks something very much similar to, I mean, this is just dqp over 2 pi cube times 1 over 2 p 0, because this m will cancel with this m, and then this p slash plus m alpha beta e to the power minus I p dot x minus y. If this p slash plus m alpha beta was not there, then we are very much familiar with this expression, right? We gave a name for this. We said that this is nothing but delta plus of x. So, if you recall the derivation of propagator in the scalar field theory, then when you take the Klein-Gordon field, this is what you get as a result. So, delta plus of x, I will use the notation that we have used earlier, is equal to minus I dq p over 2 pi cube 2 omega p e to the power minus I p dot x. Okay. So, however, this is not quite so, because I have this expression here, but let us consider this quantity. So, delta plus x minus y here is, that will be x minus y. To get p slash plus m, what I can do is that I can, for example, if I consider I del mu of delta plus x minus y, then this will give me minus I dqp over 2 pi cube 2 omega p, and del mu will give me a factor of minus I p mu. So, minus I p mu e to the power minus I p dot x minus y, right. There is an additional I here, right. There is a minus I, and then there is an I because of this I here. This minus I is because of this, and this I p mu because there is a minus I here. So, as a result, what I have here is a minus I dqp over 2 pi cube 2 omega p, and then p mu is the power minus I p dot x minus y. This is what I get for this one. Therefore, if you consider this quantity I, gamma mu del mu plus m acting on delta plus of x minus y, then what do you get? So, this is precisely equal to this quantity, right, with a factor of minus I, or there is no minus I? There is a minus I. So minus I times psi alpha plus of x psi beta minus of y. Okay. So, similarly you can compute the other term, which is nothing but psi alpha minus anti-commutator of psi alpha minus of x and psi bar beta plus of y most of the relations are identical. All you will get here is delta minus in the place of delta plus. Therefore, the anticommutator psi of x, psi bar of y, which is the sum of these two terms, will be given by I times I gamma mu del mu plus m delta plus of x minus y plus delta minus of x minus y, which we have defined to be delta of x minus y, right. So, this is the notation that we have used. The reason I expressed it in this form is because we already know that when we consider the commutation relation phi of x, phi dagger of y, right, in the complex scalar field theory, what we got is I delta x minus y, and then this delta was 0. What we have shown earlier is this delta of x minus y is actually 0 when x minus y is actually, or x and y are actually separated by a space like separation. So, here we can use the same argument, exactly same argument. If x and y are space like with respect to each other, then this delta actually vanishes, therefore, the whole thing in the right hand side vanishes. So, causality is not violated here because of this. On the other hand, if you had in this theory, if you had considered commutation relations in addition in place of the anti-commutation relations, you would have got a relative minus sign in between, and then you would not have got this delta of x here. If you explicitly evaluate the commutation by using the fact that the fields actually obey equal time commutation relation instead of the anti-commutation relations, then you will get a different answer here, which will not be 0 when x and y are space like separated. Therefore, the causality will be violated if you consider for a spin half particle, if you consider equal time commutation relations instead of the equal time anti-commutation relations. That is one of the reasons. So, there are various reasons. One of them is, of course, the spectrum is not bounded from below, okay. And then the second thing is the spin half particles will not obey the Fermi-Dirac statistics, and finally, the causality will be violated if you consider commutation relations instead of the anti-commutation relations. Okay, so we have we will denote this quantity to be whatever we have here, the anti-commutator of psi alpha plus and psi beta minus. I will denote this quantity as S plus of x minus y. So, S plus alpha beta of x minus y. Similarly, here you will have S minus alpha beta of x minus y for this guy. So, this quantity here I will denote as S of x minus y, where S of x minus y is simply S plus x minus y plus S minus of x minus y. So, you take delta plus and then you act this operator here on it, what you will get is denoted by S plus and similar expression for S minus. You can do analogous calculation for the vacuum expectation value of time ordered product. So, time ordered product of psi of x, psi bar of y, this is what you can consider. This will give you the Feynman propagator for the Dirac spinors, which I will denote as I. So, there is an I factor here in all this definition, I times SF of x minus y, where SF x minus y is the Feynman propagator, F for Feynman, and this is nothing but theta of x0 minus y0 s plus of x minus y plus or minus theta of y0 minus x0 s minus of x minus y. This is the Feynman propagator. So, I leave it as a homework for you to compute the vacuum expectation value of this time order product, and then show that this is in fact equal to this quantity. All right. Any question up to now? Okay, so now let us look at the spectrum in more detail, and then let us see what are the quantum numbers that we need to level the states. So, we have already the anti-commutation relations C S P C R Dagger of P prime is 2 pi cube whatever, right, 2 pi cube and omega over m delta of P minus P prime, and similar relation for ds of P dr Dagger of P prime. This suggests that these C's are the annihilation operators and the C daggers are the creation operators, and then the vacuum is annihilated by CSP, this is equal to 0 for S equal to 1, 2 and for all P. Similarly, the vacuum is also annihilated by DSP for S equal to 1, 2 and for all values of P. Yeah. Yeah, there is a delta RS. Thank you. And the one particle states are, for example, created by acting these creation operators C is Dagger of P acting on this and ds Dagger of P acting on the vacuum. I have already briefly stated in the last lecture that this appearance of two different types of creation and annihilation operator implies that there exist two kinds of particles, and these two types of particles there is an additional quantum number to distinguish between these two particles, and this quantum number comes from the charge operator. We have already seen that the Dirac Lagrangian is in fact psi bar I gamma mu del mu minus m psi. This has a U1 invariance, okay, global U1 invariance. If you consider this transformation psi going to e to the power I theta times psi, then this Lagrangian density is invariant under such a transformation, and as a consequence we get a conserved current del mu J mu equal to 0, where J mu equal to psi bar gamma mu psi. This quantity is the charge operator Q. The total charge is given by d cube x. All physical quantities are considered within the normal ordering. So, this is psi bar gamma 0 psi, or this is nothing but d cube x normal order product of psi dagger psi. We know what is the mode expansion for the field psi and psi dagger for these two fields. So, we can substitute the mode expansion, we can use the anti-commutation relations here, and finally what we will get is, I will write down the expression for the charge operator. So, after you substitute the mode expansion, what you will get is Q is d q p over 2 pi cube m over p 0. Although I write p 0 in all these expressions, I assume implicitly that this p 0 is not independent, but it is omega p, which is square root of p square plus m square, right. This is the condition that we are imposing, and then sum over s C s dagger of p C s p minus d s dagger of p d s of p. Because of this minus sign here, you can show that this implies the commutation relation between Q and C s dagger of P is nothing but C s dagger of P, and the commutator of Q d s dagger of P comes with a minus ds dagger of P. As a result, if you consider a state like this, so this implies that Q acting on C s dagger P vacuum is plus C s dagger P acting on vacuum, whereas this equation here implies that the charge operator acting on ds dagger of P 0 is nothing but minus ds dagger P of 0. So, therefore, these are in our convention positively charged particles, and these are negatively charged particles because of the plus and minus sign here. Similarly, we can in addition to charge, we also have spin. Okay, so what you can show in fact is that you can choose an appropriate basis, and then I will not derive it again here. You can consider P to be along z axis and then in some suitable basis you can consider the eigenstates of J12 operator, and then I will just say that C1 dagger of P, this have eigenvalues plus half, C2 dagger of P is a state with spin minus half, B1 dagger of P is a state with spin minus half, and B2 dagger of P acting on weak ground state is a state with spin plus half. Okay. Huh? D1, thank you. D1 and D2. So, this appearance of particles of two different charges positively and negatively charged particles, suggests that there must be some symmetry which actually relates these two particles, right. If you look at their energy eigenvalues, both the energy eigenvalues for both the particles will be the same, but they have opposite charges. So, there should be some symmetry which relates particles of positive charge with particles of negative charge. It is known as the charge conjugation. Charge conjugation is a discrete symmetry, it is not a continuous symmetry, it is a discrete symmetry. There are other discrete symmetries, for example, parity is also a discrete symmetry, time reversal is a discrete symmetry, and charge conjugation is also a discrete symmetry. So, what we will do in the next few minutes is, again we will briefly discuss about these discrete symmetries, that is parity, charge conjugation, and time reversal. Okay. So, let us discuss parity first. What is the parity transformation? You consider x mu, which is x0 x under parity. Parity transformation is this transformation which just flips, it keeps the x0 coordinate the same, but it changes the sign of the spatial coordinates. So, what happens to the Dirac equation under parity? We would like the Dirac equation to be covariant under this transformation. What is the Dirac equation? It is I gamma mu del mu minus m psi of x equal to 0. So, suppose x mu goes to x mu tilde, okay, x mu prime, which is just this, then this equation has to be psi of x goes to psi prime of x prime, then psi prime of x prime should satisfy this equation I gamma mu del prime mu minus m acting on psi prime of x prime equal to 0. So, we need to know, so the question is, given this transformation, what is psi prime of x prime, so that these two equations are consistent with each other. Okay. So, let us consider the second equation. It is just I gamma 0 del 0 and minus I gamma I del I, right, minus, because I am flipping the sign of x, okay, under this transformation x0 goes to x0. So, x0 prime is x0, xi prime is minus xi under parity. Therefore, the second equation is this minus m psi prime of x prime equal to 0. Okay. Now, what I need is let us compare this with this equation I gamma 0 del 0 plus I gamma I del I minus m psi of x equal to 0. Okay. So, if you compare these two equations, then you would see that, I mean, there is this, of course, this crucial sign difference here. These two equations will be consistent with each other, provided psi prime of x prime is gamma 0 psi of x, right? Because if you substitute here for psi prime of x prime gamma 0 psi of x, then here this minus sign will be as it is, because this is m times the identity operator. But here, if you take the gamma 0 to the left, it will flip a sign, so it will become plus. But here the sign will not change, because the gamma 0 appears here again. So, therefore, psi prime of x prime must be to some phase which I will call as eta p. It must be equal to gamma 0 psi of x. If psi prime of x prime is equal to this, then the Dirac equation is covariant under parity. Now, what you do is you just use this relation, okay, and then you can derive. So, the point is that under parity P, if there exists, so you say that there exists a unitary operator P such that it takes psi of x t P dagger to psi prime of x prime t prime, which is nothing but eta p gamma 0 psi of minus x t. So, this will tell you how the parity operator acts on the creation and annihilation operators, right. So, this will, I will not derive the relation again, but this implies P acting on Bs CSP P dagger is eta P Cs of minus P, okay, and P ds of P dagger is minus eta P star ds of minus P. Where I have used the basis where gamma 0 us of minus P is us of P and gamma 0 us of P is gamma 0 Vs of minus P is minus Vs of minus P. So, you can choose a spinor basis where Us and Vs satisfies this relation, and then this implies that the creation and annihilation operators satisfy this. So, the question is, what is this operator P so that this relation is satisfied? You can check that if you consider so this is again a homework for you. P equal to exp I dq over 2 pi cube m over k0 sum over S Cs dagger of k lambda Cs of k plus pi by 2 Cs of minus k minus ds dagger of k lambda plus pi ds of k plus pi by 2 ds of minus k. So, you can explicitly check that this is in fact a unitary operator, and this operator has this property. Okay. So, you check this, you find what is the expression for eta, and also you can show that this in fact is a symmetry of the theory, in the sense that if you consider e to the power I as t, p e to the power minus I as t, it keeps the parity operator invariant. So, this is equal to p. So, just check this, I mean if this is your parity operator, then this in fact satisfies this relation and also this relation here. So, this is just to show that, I mean you have, I mean there exists a parity operator which is in fact the symmetry of the theory that we are considering. Alright, so in the next lecture we will discuss charge conjugation and time reversal, and then we will discuss interaction of the fermions with electromagnetic field. Lambda is some arbitrary parameter. So, what you will do is that you will get an expression for this phase in terms of lambda.